Hello there and welcome to the Dreamy Ocean Channel. As the day's light begins to fade, allow your body to relax completely. Unclench your jaw, let your shoulders drop and feel your breath deepen, slowing to a gentle, rhythmic tide within you. Now imagine yourself drifting weightless on the surface of a vast, calm ocean. The water beneath you is a canvas of deep indigo reflecting the distant, ancient stars. Feel the subtle, rhythmic pulse of the currents beneath you, carrying you gently, effortlessly. Allow your mind to sink not into fear, but into the profound, quiet mystery of these immense liquid realms. For within these tranquil depths, unseen by the casual eye, lies a profound transformation. Vast, oxygen-depleted zones are silently expanding, creating underwater deserts where the vibrant pulse of life falls silent. Let us now journey into these enigmatic, breathless waters, allowing their story to unfold around you, guiding you deeper into slumber. Unveiling the ocean's silent deserts. The journey into the ocean's enigmatic heart begins not with a dramatic plunge, but with a gentle, slow descent, a gradual slipping beneath the sunlit surface where life teems in vibrant, dancing hues. Imagine the water around you growing cooler, darker, the ambient light slowly dimming, transforming from a brilliant azure to a deep, profound indigo, then to an almost obsidian blackness that seems to absorb all illumination. Here, in these profound, unhurried depths, a different kind of ocean reveals itself, one that whispers not with the boisterous chorus of bustling marine communities, but with a profound, unsettling silence. It is within these vast liquid chambers that we encounter the ocean's silent deserts known to science as oxygen minimum zones, or more colloquially, dead zones. These are not places of immediate violent death, but rather regions where the very essence of life, the fundamental requirement of breath, slowly begins to ebb away. Consider the air you breathe, the invisible, life-sustaining oxygen that fills your lungs with each effortless inhalation. In the ocean, a similar vital element is dissolved within the water molecules, of O2 suspended between the water molecules, forming the lifeblood of nearly all marine creatures. For a vibrant coral reef or a bustling kelp forest, this dissolved oxygen is as essential as sunlight to a terrestrial forest, fueling the intricate metabolic processes that allow fish to swim, crustaceans to scuttle, and countless microorganisms to thrive. The ocean in its healthy state is a vast breathing entity, constantly exchanging gases with the atmosphere, circulating oxygen through its currents from the surface down to its deepest trenches. Yet in certain expansive territories beneath the waves, this vital breath becomes scarce, then thin, then altogether absent. Picture the water around you no longer teeming with schools of iridescent fish darting through the currents, no longer echoing with the clicks and whistles of unseen creatures. Instead, a profound stillness settles. The water itself might appear unchanged, clear and cool, but its invisible composition has been altered. This is the realm of hypoxia, a state where the concentration of dissolved oxygen falls to critically low levels, often less than 2 milligrams per liter. For most complex marine life, this threshold marks a boundary beyond which survival becomes impossible, a slow, suffocating embrace that drives them away or inevitably extinguishes their spark. Even deeper, or in the most extreme pockets of these zones, the oxygen can vanish entirely, giving way to a condition known as anoxia. In these anoxic waters, the very last vestiges of aerobic life, those organisms that rely on oxygen for their existence, are extinguished. What remains are often only specialized anaerobic bacteria. ancient forms of life that have adapted to flourish in the absence of oxygen, sometimes even producing toxic byproducts, like hydrogen sulfide, which lends a distinctive, often unpleasant odor to sediments brought up from these depths, a smell reminiscent of rotten eggs. Imagine this invisible chemical frontier, a boundary where the very chemistry of life shifts, where the rules of survival are rewritten by the absence of a single crucial element. These oxygen minimum zones are not a wholly new phenomenon on our planet. They have existed for eons, natural features of the ocean's vast circulation, often found in areas where deep ocean currents are sluggish, or where specific geological formations create isolated basins. For millions of years, these natural OMZs have been dynamic, expanding and contracting with Earth's grand climatic cycles, shaping the evolution of life in the deep sea, pushing species to adapt to develop extraordinary tolerances, or to migrate away from these anoxic frontiers. They are, in a sense, ancient whispering secrets held within the ocean's memory archives of past planetary conditions. However, what scientists are now observing with increasing clarity and profound concern is an unprecedented expansion of these oxygen-depleted areas, both in their size and in their frequency, extending beyond the historical boundaries of natural OMZs and encroaching upon once thriving coastal waters. This expansion transforms them from isolated natural curiosities into vast growing underwater deserts, silent voids that are actively displacing and silencing the vibrant pulse of marine biodiversity that once flourished there. Imagine the gradual, inexorable creep of a terrestrial desert, swallowing fertile lands, but transpose this image to the unseen depths, where the sand is replaced by water and the scorching sun by an absence of breath. The ocean's surface might still sparkle under the moon, its waves might still crash upon shores with their familiar lullaby. But beneath this familiar facade, the very fabric of life is undergoing a slow, quiet unraveling. Consider the vibrant world of a healthy ocean, schools of shimmering sardines moving as one, a living silver cloud. The intricate architecture of a coral reef, a city built by polyps teeming with fish of every conceivable color and form. The graceful undulations of a whale, its massive body propelled through oxygen-rich currents. The delicate dance of plankton, microscopic architects of the marine food web. All these require a steady, abundant supply of dissolved oxygen. Now, contrast this vivid imagery with the profound emptiness of a dead zone. The water is clear, yes, but eerily still. The usual symphony of clicks, chirps, and rumbles that characterize a healthy ocean is replaced by a deep, resonant silence. There are no fish schools to be seen, no large invertebrates scuttling across the seabed. The seafloor, instead of being a bustling expanse of life, is often covered in a monotonous layer of fine, dark sediment, sometimes tinged with the telltale black of iron sulfides, a chemical signature of prolonged anoxia. This sediment might be home only to specialized bacteria forming microbial mats, a stark and simple ecosystem compared to the complex layered communities of oxygenated waters. The boundaries of these silent deserts are not always sharp, dramatic walls, but often subtle, invisible gradients. Picture a slow, continuous change like the imperceptible shift in air temperature as you move from a warm room to a cooler one. Marine organisms, particularly those with higher metabolic rates like many fish, are highly sensitive to these diminishing oxygen levels. As they encounter the edge of a hypoxic zone, their bodies send urgent signals of distress. Their gills, designed to efficiently extract oxygen from water, begin to struggle. Their movements become sluggish, their breathing labored. For many, the only option is flight. a frantic search for oxygenated waters, often pushing them into unfamiliar territories or concentrating them into smaller, more vulnerable areas. Those organisms that cannot escape, or those that are sessile, fixed to the seabed like certain corals or sponges, face a different, more somber fate. They slowly suffocate. Their cells, deprived of the oxygen necessary for cellular respiration, cease to function. Their tissues begin to break down. Imagine the gradual fading of a vibrant garden, not due to drought or frost, but due to an invisible, vital element being slowly withdrawn from the very air it breathes. This is the quiet, relentless devastation that unfolds within the expanding dead zones. The unveiling of these silent deserts is not merely an academic exercise. It is a profound revelation about the changing health of our planetary ocean. It challenges our perception of the deep sea as an infinite, unchanging reservoir of life. Instead, it reveals a dynamic, vulnerable system reacting to forces both natural and increasingly anthropogenic. The term dead zone itself, while perhaps stark, serves to underscore the dramatic biological impact of these oxygen-depleted regions. It speaks to a cessation of the typical visible signs of marine vitality, a transformation of a thriving ecosystem into a barren expanse. As we continue this gentle descent, allowing our minds to drift deeper into the understanding of these phenomena, remember that the ocean's whispers are often its most profound messages. The silence of these depths is not an absence of sound, but rather the sound of an ecosystem in distress. A quiet plea carried on the currents, inviting us to listen, to comprehend, and perhaps to dream of a future where the ocean's breath can once again flow freely through all its magnificent, wondrous realms. This initial glimpse into the nature of these silent deserts sets the stage for unraveling the deeper mysteries of their causes, their expansion, and their profound implications for the very fabric of life on our blue planet. Let the soft current of this knowledge lull you further into a peaceful, reflective state as the story continues to unfold, revealing the intricate connections that bind all life, from the smallest microbe to the largest ocean in one grand interconnected system. A history of oxygen's retreat. As our awareness drifts gently from the immediate presence of these silent deserts, let us now journey backward through the deep currents of time, allowing the mind to float effortlessly across eons, to understand that the ocean's breath has not always been a constant, unwavering presence. The echoes of oxygen's retreat are not merely a phenomenon of our modern era, but resonate through the very geological history of our planet, whispering tales of ancient oceans that were in many ways profoundly different from the vibrant, oxygen-rich waters we cherish today. Consider for a moment the primordial Earth, a world still coalescing, still finding its rhythm billions of years before the emergence of complex life as we know it. In those infancy stages of our planet, the atmosphere itself held very little free oxygen. The oceans, vast and enigmatic, reflected this scarcity. Many of the early seas were largely anoxic, their depths devoid of the life-giving gas, save for the regions where primitive photosynthetic bacteria, the earliest architects of oxygen production, began their slow, transformative work. These were waters dominated by anaerobic microorganisms, strange and resilient life forms that thrived in the absence of oxygen, sometimes even in the presence of chemicals that would be toxic to most modern organisms. Imagine a planetary ocean, vast and deep, shimmering under a sun that shone through a different sky, its internal chemistry driven by forces that predate our very understanding of breathable air. Then, slowly over immense stretches of geological time, a profound transformation began. The Great Oxidation Event, a pivotal moment in Earth's history, saw the gradual accumulation of oxygen in the atmosphere and oceans primarily through the tireless work of cyanobacteria. This was a slow, majestic process taking hundreds of millions of years, fundamentally reshaping the planet and paving the way for the evolution of more complex oxygen-dependent life. But even after this monumental shift, the ocean's oxygen levels were never entirely static. Throughout Earth's long dynamic history, there have been periods of profound, widespread ocean deoxygenation events, so significant that they leave indelible marks in the geological record, like silent, dark chapters etched into the planet's memory. Scientists refer to these as oceanic anoxic events, or OAEs. Picture a time perhaps 100 million years ago during the Cretaceous period when colossal volcanic eruptions filled the atmosphere with greenhouse gases, causing the Earth's climate to warm dramatically. As the planet heated, ocean temperatures rose, reducing the solubility of oxygen in the water. Much like a warm drink holds less dissolved gas than a cold one. Concurrently increased rainfall on land would have intensified weathering, washing vast quantities of nutrients derived from eroding rocks into the oceans. Imagine these ancient oceans swelling with an overabundance of nutrients. This influx would have fueled explosive blooms of marine algae and other phytoplankton microscopic life forms, multiplying at an astonishing rate, coloring the surface waters in vast, vibrant patches. But just as quickly as they bloomed, these organisms would die, their tiny bodies sinking slowly like a gentle snowfall through the water column. As this immense organic matter settled into the depths, it became a colossal feast for oxygen-consuming bacteria. These decomposers, working tirelessly, would strip the deep waters of their precious oxygen, consuming it faster than ocean circulation could replenish it from the surface. The result was a profound, suffocating anoxia that spread across vast stretches of the ancient ocean, sometimes for hundreds of thousands or even millions of years. The geological evidence for these OAS is preserved in the distinctive layers of black shale found in rock formations around the world. These black shales are rich in organic carbon, the undecayed remains of the organisms that sank to the anoxic seafloor where there was no oxygen to fuel their decomposition. They are like dark, silent archives holding the secrets of a breathless past, testifying to periods when marine life, particularly in the deep, faced immense challenges leading to significant shifts in biodiversity, and in some cases contributing to mass extinction events. Yet paradoxically, these events also laid down the organic matter that over geological time transformed into the very fossil fuels that power our modern world. Even in more recent geological history, long before the industrial age began to reshape our planet, certain regions of the ocean naturally harbored persistent oxygen minimum zones. These natural OMZs were typically found in areas where ocean currents were sluggish, preventing the efficient mixing of oxygen-rich surface waters with the deeper layers. The eastern tropical Pacific, for instance, has long been home to one of the largest and most intense natural OMZs, a vast stretch of ocean where oxygen levels naturally dip to near anoxic conditions at certain depths. Similarly, the Arabian Sea, due to its unique oceanographic setting and high biological productivity, also exhibits a pronounced natural oxygen minimum zone. These zones, while inhospitable to many forms of life, are not entirely barren. Over millions of years, specialized species have evolved remarkable adaptations to survive and even thrive in these low oxygen environments, developing unique metabolic pathways or physiological tolerances that allow them to endure where others cannot. They are a testament to life's profound adaptability, a quiet demonstration of evolution's patient work. These natural OMZs relatively stable and geographically defined for millennia, provide a baseline, a subtle whisper from the past, against which we can measure the profound changes unfolding in our contemporary oceans. They remind us that the ocean is a dynamic system constantly in flux, but also highlight the delicate balance that sustains its vast biodiversity. The turning point, the moment when the echoes from the past began to merge with a new, human-driven crescendo, arrived with the dawn of the Industrial Revolution and the subsequent intensification of human activities across the globe. As societies industrialized, as populations grew, and as agricultural practices became more intensive, an invisible burden began to flow from the land into the ocean. This burden was primarily an overload of nutrients, nitrogen and phosphorus, originating from agricultural fertilizers, untreated sewage, and industrial discharges. Imagine the rivers once carrying primarily natural sediments and dissolved minerals, now becoming conduits for these excess nutrients, flowing steadily, inexorably into coastal waters, estuaries, and enclosed seas. This phenomenon, known as cultural eutrophication, began to artificially fertilize vast stretches of the ocean's surface. Just as in the ancient oases, this nutrient influx triggered immense unnatural blooms of phytoplankton. These microscopic plants, gorging on the sudden abundance, multiplied with astonishing speed, forming dense verdant clouds in the sunlit surface waters. But the cycle of life and death in these artificially enhanced ecosystems became tragically unbalanced. As these massive algal blooms eventually died, their organic matter sank to the seabed in unprecedented quantities. The oxygen-consuming bacteria in the deeper waters, and sediments now presented with an overwhelming feast, began to consume dissolved oxygen at rates far exceeding its replenishment. This marked the genesis of many of the modern coastal dead zones regions, where human activity directly initiated the process of deoxygenation. The first clear observations of these human-induced dead zones began to emerge in the mid-20th century as scientific monitoring capabilities improved. Scientists patiently collecting data from research vessels and coastal stations started to notice alarming trends, persistent areas of low oxygen, particularly in enclosed or semi-enclosed bodies of water, like the Baltic Sea, the Black Sea, and the Gulf of Mexico. These were not the ancient deep ocean OMZs, but new expanding zones of hypoxia, often directly linked to major river systems, draining densely populated or agricultural regions. The evidence accumulated slowly, painstakingly, through countless water samples, sediment cores, and observations of declining fish populations. Each data point was a quiet confirmation, a subtle but undeniable signal of a profound change occurring beneath the waves. As the decades progressed, the number and extent of these coastal dead zones continued to grow, like silent advancing shadows, spreading across the continental shelves. The 21st century has seen an acceleration of this trend, with hundreds of new dead zones identified globally from the coasts of Europe to Asia and across the Americas. This rapid expansion is distinct from the slow geological rhythm of ancient OAS. It is a change occurring within the span of human generations, driven not just by nutrient runoff, but increasingly exacerbated by the warming of our planet. The ocean, like a vast living memory, holds these echoes from the past, reminding us that oxygen's retreat is a story that has unfolded before. But the current chapter is unique, characterized by a speed and global reach that sets it apart. The whispers of ancient anoxia now blend with the louder, more urgent warnings of a modern deoxygenation event, one that demands our attention and understanding. As we reflect on this long history, Allow your mind to absorb the profound interconnectedness of Earth's systems, from the deep past to the present moment, letting the gentle ebb and flow of this knowledge guide you deeper into a state of serene contemplation. Deconstructing oxygen's disappearance. As our journey through time recedes, leaving behind the echoes of ancient anoxic events and the nascent whispers of human influence, let us now turn our focus to the intricate, invisible ballet of chemistry and physics that governs the ocean's breath. Imagine the water around you not as a simple, uniform liquid, but as a complex, dynamic solution, a living medium where every molecule plays a vital role. The disappearance of oxygen in these silent depths is not a sudden, dramatic vanishing act, but rather a slow, relentless chemical process, a delicate balance tipped by a confluence of interwoven factors. At the very surface of the ocean, where the vast liquid expanse meets the boundless atmosphere, a ceaseless exchange occurs. Picture the gentle undulations of the waves, the subtle ripples stirred by a passing breeze. With each tiny crest and trough, countless molecules of oxygen from the air are absorbed into the topmost layer of the water. This process, known as diffusion, is the ocean's primary way of breathing from the atmosphere, a constant, quiet absorption of life-giving gas. The colder the water and the more turbulent its surface, the more efficiently it can dissolve and hold this atmospheric oxygen, much like a chilled, effervescent drink retains its bubbles more readily than a warm, flat one. Beyond this atmospheric exchange, another profound source of oxygen lies within the ocean itself, the tireless work of microscopic life. Consider the vast, unseen forests of phytoplankton, tiny plant-like organisms that drift near the sunlit surface. These chlorophyll-rich entities, harnessing the energy of sunlight, perform photosynthesis, the same fundamental process that trees and grasses carry out on land. They absorb carbon dioxide from the water and release oxygen as a byproduct, bathing the upper layers of the ocean in a fresh, vital supply of the gas. This biological production of oxygen is a cornerstone of marine life, fueling the food webs that sustain everything from the smallest copepod to the largest whale. So if oxygen is constantly entering the ocean from the atmosphere and being produced by photosynthesis, why does it disappear in certain regions? The answer lies in the equally relentless processes that consume it. The most significant consumer of dissolved oxygen in the ocean is respiration. Every living organism, from the largest fish to the smallest bacterium, needs oxygen to break down food and release energy, a process akin to our own breathing and metabolism. When fish swim, when corals build their intricate structures, when crabs scuttle across the seabed, they are all drawing upon the dissolved oxygen around them. However, the most profound drain on the ocean's oxygen supply comes from the decomposition of organic matter. Imagine the endless cycle of life and death in the ocean. Microscopic plankton, larger marine animals, and even fragments of terrestrial plants washed in from land all eventually die. Their remains, often tiny, delicate particles, begin a slow, silent descent through the water column, forming what oceanographers poetically call marine snow. This continuous shower of organic debris drifts downward deeper and deeper into the dimly lit and eventually dark realms where sunlight cannot penetrate. As this marine snow descends, it becomes a colossal feast for an army of microscopic decomposers, bacteria and archaea that reside throughout the water column and particularly on the seafloor. These tireless microorganisms play an essential role in breaking down dead organic matter, recycling nutrients back into the ecosystem. But in doing so, they perform cellular respiration just like larger animals, and this process consumes vast quantities of dissolved oxygen. The more organic matter that sinks, the more oxygen these decomposers consume. It is a fundamental, essential process, but one that, when pushed out of balance, can become a silent engine of deoxygenation. Now, layer upon this biological consumption the critical role of ocean circulation. The ocean is not a static bathtub. It is a dynamic, constantly moving system driven by colossal currents that circulate water masses across the globe, from the frigid poles to the warm equator, and from the surface to the abyssal plains. These currents act like the planet's circulatory system, carrying oxygen-rich waters from the surface down into the depths and distributing it horizontally across vast distances. When these currents are vigorous and well mixed, oxygen can be efficiently replenished even in deep waters. But in certain regions or under specific conditions, this vital circulation can slow or become blocked. Picture layers of water of different temperatures or salinities, like oil, and water refusing to mix. This phenomenon is called stratification. Warmer, less dense water tends to float on top of colder, denser water. Similarly, fresher water can sit atop saltier water. When the ocean becomes strongly stratified, these distinct layers act as invisible barriers, preventing the vertical mixing that would otherwise bring oxygen from the surface down to the deeper, oxygen-depleted waters. It's like a lid being placed on a pot, sealing off the lower layers from fresh air. Without this crucial vertical mixing, the oxygen consumed by decomposition in the deeper layers cannot be easily replaced, leading to a gradual, inexorable decline in oxygen concentration. The physical properties of water itself also play a crucial role in this breathless chemistry. Remember how warmer water holds less dissolved gas. As the planet's climate warms the surface, waters of the ocean absorb more heat. This warming has a direct, profound effect. It reduces the solubility of oxygen in the water. A warmer ocean simply cannot hold as much oxygen as a cooler one, even if all other factors remain constant. This means that even before any biological consumption occurs, the ocean's capacity to store oxygen is diminished. Furthermore, ocean warming tends to enhance stratification. As surface waters become warmer, the density difference between them and the cooler, deeper layers increases, making it even harder for vertical mixing to occur. This creates a powerful positive feedback loop. Warming reduces oxygen solubility and hinders its replenishment, trapping the deeper waters in a state of diminishing breath. When oxygen levels in the water fall below a critical threshold, typically around 2 milligrams per liter, the environment becomes hypoxic. At this point, most complex marine life, from fish to crabs to many types of worms, struggles to survive. Their metabolic processes are severely hampered, their growth rates slow, and their reproductive capacities diminish. They literally gasp for breath in an invisible, watery medium. Many will flee if they can, seeking out the oxygenated fringes of these zones, creating squeeze play effects where populations are unnaturally concentrated, making them more vulnerable to predation or fishing pressure. If oxygen levels continue to fall, eventually reaching a state of complete absence, the water becomes anoxic. In these truly breathless waters, the very chemistry of life undergoes a radical shift. The bacteria that thrive here are no longer those that rely on oxygen for respiration. Instead, anaerobic microorganisms take over, employing different chemical pathways to break down organic matter. Some of these pathways, like sulfate reduction, produce highly toxic byproducts, most notably hydrogen sulfide, a gas notorious for its pungent, rotten egg smell. This hydrogen sulfide is poisonous to most aerobic life, creating an even more hostile environment and further cementing the dead, nature of these zones. It can also react with metals in the sediment, forming black precipitates, leaving a visible dark signature on the seafloor. Moreover, anoxic conditions in the sediments can trigger the release of nutrients, such as phosphorus, that were previously locked away. This released phosphorus can then diffuse back into the overlying water column, where it acts as a powerful fertilizer, fueling even more phytoplankton blooms at the surface. This creates another insidious feedback loop. Deoxygenation leads to nutrient release, which leads to more blooms, more sinking organic matter, and thus even more oxygen consumption, deepening and expanding the dead zone. It's a self-perpetuating cycle of decline, a silent chemical spiral into breathlessness. The deconstruction of oxygen's disappearance reveals a complex interplay of biological demand, physical circulation, and chemical properties, all exquisitely sensitive to changes in temperature and nutrient input. It is a story told not in words, but in the subtle shifts of molecular concentrations in the invisible boundaries between life and stillness. As we unravel these intricate chemical threads, allow your mind to appreciate the profound interconnectedness of these processes, letting the rhythmic explanation of science guide you deeper into a state of calm understanding as the ocean's breathless chemistry continues to unfold in your mind's eye. Tracing the flow of nutrient overload. As our understanding deepens into the intricate chemistry that governs the ocean's breath, let us now turn our attention to the silent architects of this imbalance, the invisible pathways that carry a profound burden from the land to the sea. Picture, if you will, the vast undulating surface of our continents, a patchwork of forests, mountains, and most predominantly, the meticulously ordered fields of human agriculture stretching beneath the sun in geometric precision. It is from these terrestrial realms, often far removed from the ocean's edge, that a quiet, relentless flow begins a journey of microscopic particles and dissolved chemicals that will ultimately reshape the marine world. The story of the river's burden begins with two fundamental elements: nitrogen and phosphorus. These are the very building blocks of life-essential nutrients that fuel the growth of plants and animals alike. In a natural, undisturbed ecosystem, nitrogen cycles through the atmosphere, soil, and living organisms, while phosphorus, primarily derived from the weathering of rocks, slowly makes its way through terrestrial and aquatic environments. These natural flows are balanced, a delicate equilibrium maintained over eons, ensuring that no single element overwhelms the system. However, with the expansion of human civilization, particularly over the last 2 centuries, this ancient balance has been profoundly disrupted. Our intensive agricultural practices, designed to feed a burgeoning global population, rely heavily on synthetic fertilizers. Imagine the colossal factories quietly churning out tons upon tons of chemical compounds rich in nitrogen and phosphorus. Then picture these compounds being spread across millions of acres of farmland, nourishing crops to maximize yield. While essential for food production, not all of these applied nutrients are absorbed by the plants. A significant portion remains in the soil unbound, waiting for the next rain, when the gentle patter of rain begins to fall, or when irrigation systems release their steady flow. These excess nutrients, dissolved in the water, begin their slow, inexorable journey. They seep through the soil, percolating downward, eventually reaching the groundwater table. Or more directly, they are carried across the land's surface as runoff, flowing into small ditches, then into meandering streams, and finally into the larger, more powerful arteries of the land, the rivers. Picture these countless invisible molecules once intended to nourish a field of corn or wheat, now embarking on an unintended voyage carried by the flowing water, a silent, unseen cargo. But agriculture is not the sole contributor to this nutrient overload. Our urban centres with their vast populations also generate immense quantities of wastewater. Imagine the intricate, unseen networks of pipes beneath our cities, carrying the daily flow of human waste from homes and businesses. While modern wastewater treatment plants are designed to remove many pollutants, even the most advanced systems often struggle to completely strip out dissolved nitrogen and phosphorus before the treated effluent is discharged into rivers or directly into coastal waters. In many parts of the world, particularly in rapidly developing regions, wastewater treatment infrastructure may be inadequate or entirely absent, allowing raw or minimally treated sewage to directly enter aquatic systems carrying a concentrated dose of these life-altering nutrients. Furthermore, certain industrial processes can also contribute to the nutrient load, releasing effluents rich in nitrogen and phosphorus into waterways. Even atmospheric deposition, where nitrogen oxides released from the burning of fossil fuels fall back to Earth, as acid rain or dry particles can contribute to the overall nutrient burden, particularly in regions downwind from major industrial or urban areas. It is a cumulative effect, a multitude of human activities, each contributing its share, that collectively overwhelms the natural capacity of the land and its waters to process these elements. As these nutrient-laden rivers flow towards the sea, they act as vast, slow-moving conveyor belts, collecting and concentrating the agricultural runoff, urban sewage, and industrial discharges from their entire watershed. A single river like the Mississippi in North America or the Yangtze in Asia drains enormous land masses encompassing countless farms, towns, and cities. By the time these colossal rivers reach their estuaries, the concentration of dissolved nitrogen and phosphorus can be orders of magnitude higher than natural background levels. Imagine the sheer volume of water carrying this invisible chemical cargo finally merging with the vastness of the ocean. Upon entering the relatively calm, often enclosed waters of estuaries, bays, and coastal shelves, these excess nutrients encounter a new environment. Here, the conditions are often ideal for a profound biological reaction. The shallow depths allow ample sunlight to penetrate, and the reduced salinity creates a distinct layering of water, which can further trap nutrients in the upper sunlit zones. For the microscopic phytoplankton, the primary producers at the base of the marine food web, this sudden influx of nitrogen and phosphorus is like an unlimited, intoxicating feast. What follows is often a rapid, uncontrolled proliferation of these tiny plant-like organisms, an event known as an algal bloom. Picture the surface waters, once a clear, translucent blue or green, slowly transforming. They might take on a cloudy, murky appearance, then a distinct green hue, sometimes even shades of red or brown, depending on the species of algae dominating the bloom. These blooms can be so dense and extensive that they form a thick, opaque blanket across the water's surface, stretching for miles. They are a visual manifestation of the nutrient overload, a verdant explosion of life, but one that carries within it the seeds of destruction for the ecosystem below. This dense blanket of algae, while thriving in the surface waters, also casts a deep, unforgiving shadow. Imagine the delicate seagrass meadows and the intricate coral reefs that lie beneath organisms that rely on sunlight for their own photosynthesis. The thick algal bloom above acts like a colossal living parasol, blocking out the vital sunlight. Deprived of light, these submerged plants and corals begin to sicken and die, their vibrant colors fading to a dull, lifeless gray or brown. The intricate habitats they provide for countless fish, crustaceans, and other invertebrates slowly disappear, leaving behind a barren skeletal landscape. But the most profound impact of these algal blooms occurs when they eventually reach the end of their explosive life cycle. Just as quickly as they bloomed, these billions upon billions of microscopic algae begin to die. Their tiny bodies, along with other organic matter from the land, slowly sink through the water column like a relentless organic snowfall. As this immense quantity of dead organic material settles onto the seabed and into the deeper waters, it becomes an overwhelming feast for the decomposer bacteria and other microorganisms that reside there. Recall from our previous discussion the tireless work of these bacteria consuming dissolved oxygen as they break down organic matter through respiration. In the presence of such an enormous, unnatural influx of dead algae, their metabolic activity skyrockets. They consume oxygen at an accelerated rate far faster than it can be replenished by surface diffusion or by the sluggish currents in these often stratified coastal waters. The delicate balance is irrevocably tipped. The oxygen levels in the bottom waters and sediments begin to plummet. From a healthy, life-sustaining concentration, they drop steadily, relentlessly first into hypoxic conditions, where oxygen is dangerously low, and then, in the most severe cases, into anoxic conditions where oxygen is entirely absent. This is how the rivers burden the seemingly innocuous flow of excess nutrients from our lands directly engineers the creation of these silent, suffocating dead zones in our coastal oceans. The consequences are profound. The once vibrant ecosystems teeming with diverse marine life are transformed into barren underwater deserts. Fish, if they can flee the suffocating embrace of these low-oxygen waters. Those that cannot escape, or those like clams, oysters, and slow-moving bottom dwellers, perish their bodies, sinking into the anoxic sediments, further fueling the cycle of decomposition. The rich biodiversity that defines healthy coastal waters gives way to a desolate landscape populated only by the most resilient specialized bacteria capable of surviving in the absence of breath. This tracing of the flow from the quiet fields and bustling cities through the winding rivers and into the waiting ocean reveals a deep and often unseen connection between human activity on land and the health of our marine environments. It is a story of unintended consequences where the pursuit of human sustenance and comfort inadvertently creates vast underwater voids. As these scientific insights gently settle in your mind, allow the profound interconnectedness of land and sea to deepen your contemplation, guiding you further into a state of peaceful understanding as the silent current of knowledge carries you onward. How? A changing climate fuels the void, as the silent burden of nutrients flows from land to sea, creating localized pockets of breathlessness. Another far more pervasive force is subtly, inexorably reshaping the global ocean, an invisible embrace of warmth that fuels the void from its deepest reaches to its sunlit surfaces. This is the profound influence of a changing climate, a slow planetary fever that diminishes the ocean's very capacity to breathe, amplifying the existing stresses and extending the reach of the dead zones across vast liquid territories. Imagine the colossal heat energy accumulating in our planet's atmosphere, a consequence of increased greenhouse gases radiating downward, warming the air and crucially warming the surface waters of the ocean. This warming, though often imperceptible to our senses on a daily basis, has a fundamental physical consequence for dissolved gases. Consider a simple experiment: a glass of cold water with ice and a glass of warm water. If you were to drop a fizzing tablet into each, the cold water would retain its effervescence for much longer. its bubbles slowly rising while the warm water would quickly lose its fizz. This everyday observation illustrates a critical scientific principle. Gases, including oxygen, are less soluble in warmer liquids. Thus, as the ocean's surface waters absorb more heat, their inherent capacity to hold dissolved oxygen diminishes. It's as if the very fabric of the water itself becomes less able to cradle the vital oxygen molecules. Even before any biological consumption or circulation changes come into play, a warmer ocean is by its very nature a less oxygen-rich ocean. This effect is not confined to specific areas but is a global phenomenon, a quiet, pervasive reduction in the ocean's oxygen reservoir, like a slow, steady exhalation that is not fully compensated by a subsequent inhalation. But the warming embrace extends its influence beyond mere solubility. It profoundly impacts the ocean's stratification, the layering of water masses of different densities. Picture the vast expanse of the ocean typically characterized by layers warmer, lighter water near the surface and colder, denser water in the depths. This natural layering is crucial. In healthy, well-mixed oceans, particularly in temperate and polar regions, seasonal cooling and powerful winds can break down this stratification, allowing oxygen-rich surface waters to sink and mix, with deeper layers effectively ventilating the entire water column. This process is like the ocean taking a deep, cleansing breath, circulating fresh air throughout its vast lungs. However, as the surface waters warm, the temperature difference between the surface and the deeper, cooler layers becomes more pronounced. This increased temperature gradient leads to greater density stratification. The warmer, lighter surface water becomes even more buoyant, creating a stronger, more stable barrier that resists mixing with the cooler, denser water below. Imagine a thick, invisible blanket settling over the deeper ocean and sealing it off from the oxygenated surface. This enhanced stratification acts like a persistent lid, preventing the vital downward transport of oxygen. The deeper waters continuously consuming oxygen through the respiration of decomposers become increasingly isolated, their oxygen supply slowly dwindling without the possibility of replenishment from above. This is a slow, insidious suffocation driven by the very warmth that initially seems so benign. Furthermore, a changing climate has the potential to alter the grand planetary-scale ocean circulation patterns, the colossal conveyor belts that transport heat nutrients and, crucially, oxygen around the globe. Scientists theorize that as polar ice melts and fresh water enters the ocean, it could potentially disrupt these delicate circulation systems, particularly the deep ocean currents that originate in the polar regions. These deep currents are vital for ventilating the abyssal ocean, carrying oxygen-rich water from the surface down to the greatest depths. If these currents were to slow or weaken the oxygen supply to vast stretches of the deep ocean, could be severely curtailed, leading to the expansion and intensification of natural oxygen minimum zones, transforming them from dynamic features into stagnant, breathless voids. This is a long-term, slow-motion change, but one with profound, far-reaching implications for the entire marine ecosystem. Beyond these physical changes, the warming embrace also subtly influences biological processes. Consider the metabolic rates of marine organisms. Just as our own bodies speed up or slow down with changes in temperature, so too do the metabolic processes of marine life. In warmer waters, the metabolic rates of many organisms, including the oxygen-consuming bacteria that decompose organic matter, tend to increase. This means that in a warmer ocean, these decomposers consume oxygen more rapidly. Thus, even if the amount of organic matter sinking to the depths remained constant, the rate at which oxygen is stripped from the water would accelerate, further exacerbating deoxygenation. It's a double-edged sword. The ocean holds less oxygen, and what oxygen it does hold is consumed more quickly. The warming of the climate also interacts with the issue of nutrient overload, creating a dangerous feedback loop. As global temperatures rise, weather patterns can become more extreme. This often translates to more intense rainfall events in many regions. Imagine a sudden torrential downpour washing over agricultural fields that are already laden with excess fertilizers. These intense rains are far more efficient at flushing nutrients from the land into rivers and ultimately into coastal waters, intensifying the very nutrient runoff that fuels algal blooms and coastal dead zones. So the warming climate doesn't just create new dead zones, it also amplifies the severity and extent of existing ones, particularly in vulnerable coastal areas already grappling with anthropogenic nutrient pollution. Moreover, warmer temperatures can also extend the growing season for terrestrial plants, and by extension, for agricultural crops. While seemingly beneficial for food production, this can lead to an increased reliance on fertilizers over longer periods, further contributing to the overall nutrient burden carried by rivers to the sea. The cycle becomes more entrenched, more difficult to break as human activities and natural climate shifts conspire to diminish the ocean's vitality. The insidious nature of this warming embrace lies in its pervasive, often invisible influence. Unlike a sudden oil spill or a dramatic flood, the gradual warming of the ocean is a slow-motion transformation, often detectable only through meticulous scientific monitoring over decades. Yet its cumulative effect is profound. It reduces the ocean's inherent capacity to hold oxygen. It creates stronger barriers to oxygen replenishment through stratification. It potentially disrupts the deep-sea ventilation currents, and it accelerates the biological consumption of oxygen. Each of these factors, individually significant, becomes even more potent when combined synergistically, driving the expansion and intensification of oxygen minimum zones across both coastal and open ocean environments. Scientists using sophisticated models and collecting data from a global network of sensors are piecing together a comprehensive picture of this silent crisis. They observe that the volume of ocean water with unnaturally low oxygen levels has expanded significantly in recent decades, particularly in the open ocean where nutrient runoff is less of a direct factor. This expansion is directly attributable to the warming of the planet, a testament to the far-reaching consequences of climate change on the delicate balance of marine ecosystems. As we allow these complex scientific connections to settle gently in our minds, let us recognize that the ocean's breath is not merely a local phenomenon, but a global one, intricately linked to the overall health of our planetary climate. The warming embrace, while seemingly gentle, is a powerful force quietly transforming vast stretches of our blue planet into silent, breathless voids. This understanding, profound and sobering, invites a deeper contemplation of our interconnectedness with the natural world, gently guiding you further into a state of serene reflection as the subtle currents of knowledge continue to carry you into deeper slumber. Mapping the contours of oxygen minimum zones, having drifted through the profound understanding of how a warming embrace and the river's silent burden conspire to diminish the ocean's breath, our journey now turns to the very act of discovery itself. How do we, as human observers from the surface world, perceive these invisible, suffocating voids that lie beneath the shimmering expanse? How do we map the unseen contours of oxygen minimum zones, delineating their silent presence in a medium that yields no visual clues to its chemical composition? Imagine the vast liquid expanse of the ocean stretching endlessly in every direction. From our vantage point above, its surface appears a uniform blue, perhaps dappled with sunlight, or textured by the rhythmic sway of waves. But beneath this familiar facade, the ocean holds secrets in its invisible chemistry, secrets that only patient, meticulous observation can reveal. The dissolved oxygen, the very essence of marine breath, is a gas colorless and odorless in water, its presence or absence undetectable by the unaided eye. To map these silent deserts, scientists must employ an array of sophisticated tools, each designed to pierce the watery darkness and measure the very breath of the deep. In the nascent days of oceanography, the quest for understanding the ocean's internal chemistry began with simple yet profound acts of sampling. Picture a sturdy research vessel, its deck, a hive of quiet activity slowly traversing the ocean's surface. From its side, a cable, thick and strong, would unwind, lowering a series of specialized bottles, often made of brass or plastic, known as Nansen bottles, deep into the water column. Each bottle was designed to be lowered open, allowing water to flow freely through it until it reached a predetermined depth. Then, with a precisely timed signal, a small weight called a messenger would slide down the cable, triggering a mechanism that would snap the bottle shut, capturing a pristine sample of water from that exact depth. Once brought back to the surface, these water samples would be carefully drawn and immediately subjected to a chemical analysis known as the Winkler titration method. This delicate procedure, involving a series of chemical reagents, would cause the dissolved oxygen in the water to react, producing a measurable color change, allowing scientists to meticulously calculate the precise concentration of oxygen present in that specific sample. Imagine the painstaking effort, the repetitive process of lowering bottles, retrieving them, and performing these intricate chemical tests. One depth at a time, one location at a time, slowly, patiently building a rudimentary vertical profile of oxygen levels. These early efforts were like painting a vast, unseen landscape with tiny individual brushstrokes, each one a precious piece of data contributing to the nascent understanding of the ocean's internal respiration. As scientific understanding and technology advanced, the process of mapping these invisible contours became more sophisticated, moving from discrete individual samples to continuous real-time measurements. Enter the CTD rosette, a marvel of modern oceanographic instrumentation. Picture a large circular frame, often several meters in diameter, adorned with numerous scientific sensors, and surrounded by a ring of sample bottles, similar in function to the Nansen bottles, but far more advanced. The core of this instrument is the CTD itself, which stands for conductivity, temperature, and depth. These three fundamental properties are measured continuously as the rosette is slowly lowered through the water column, sending a constant stream of data back to the research vessel via an armored cable. Crucially mounted alongside the CTD are specialized oxygen sensors. These electrochemical probes are designed to precisely measure the concentration of dissolved oxygen in the surrounding water, often in real time, providing a continuous high-resolution profile from the surface down to the deepest parts of the ocean. Imagine this sophisticated array descending through the water, silently transmitting its findings, revealing the gradual decline of oxygen with increasing depth, charting the invisible boundaries where life's breath begins to thin and then, perhaps, to vanish altogether. The data collected by CTD rosettes allows scientists to create detailed vertical profiles, like a cross-section of the ocean's respiratory system, revealing the exact depths at which hypoxic and anoxic conditions begin and how thick these breathless layers truly are. But the ocean is a vast three-dimensional realm, and ship-based surveys, while precise, are inherently limited in their spatial and temporal coverage. To truly map the global extent and dynamic nature of oxygen minimum zones, oceanographers turn to autonomous technologies. Picture a fleet of silent, independent robotic explorers, drifting through the ocean's vastness tirelessly, collecting data where human vessels cannot constantly be. One of the most transformative of these technologies is the Argo Float Network. Imagine thousands of these cylindrical torpedo-shaped robots, each about the size of a person, quietly drifting beneath the surface of the world's oceans. Every 10 days, a typical Argo float begins a programmed dive, descending slowly to depths of up to 2,000 meters, or even 4,000 meters for some specialized floats. During its ascent back to the surface, it continuously measures temperature, salinity, and increasingly dissolved oxygen, along with other parameters. Once at the surface, it transmits its collected data via satellite to land-based receiving stations before quietly descending again to drift at its parking depth, awaiting its next mission. These floats provide an unprecedented near-global year-round picture of the ocean's interior, allowing scientists to observe the expansion and contraction of oxygen minimum zones over vast areas and through all seasons, revealing their dynamic, shifting nature. For more localized, sustained observations, particularly in the complex, shallower waters of coastal regions, where many dead zones are concentrated, scientists deploy autonomous underwater gliders and other autonomous underwater vehicles, or AUVs. Imagine a sleek, wing-shaped robot silently propelled through the water by subtle changes in its buoyancy, gracefully gliding in a sawtooth pattern, ascending and descending constantly, collecting data. These gliders can operate for weeks or even months on end, covering hundreds or thousands of kilometers, providing high-resolution maps of oxygen levels in specific, targeted areas. They are like patient, tireless scouts, meticulously charting the boundaries of coastal dead zones, revealing how they expand and contract in response to tidal cycles, seasonal changes, and human activities. Another crucial tool in mapping the temporal dynamics of OMZs are oceanographic moorings. Picture a sturdy anchor firmly planted on the seafloor, connected by a long cable to a series of submerged buoys. Along this cable, at various depths, are attached sophisticated sensors, including oxygen probes, continuously recording data over extended periods, sometimes for years. These moorings provide invaluable time series data, acting like fixed weather stations in the ocean's interior, revealing how oxygen levels fluctuate daily, seasonally, and annually at a single point, offering crucial insights into the rhythm and variability of deoxygenation. Once this vast trove of data is collected from ships, floats, gliders, and moorings, the true work of mapping begins. Scientists employ advanced computational models and visualization techniques to transform raw numbers into comprehensible contours. Imagine intricate multidimensional maps where color gradients depict the concentration of oxygen from vibrant blues, indicating healthy oxygen-rich waters, to pale greens for hypoxic conditions, and finally to deep unsettling purples or blacks for anoxic zones. These maps are not static images. They are often dynamic, animated representations showing the expansion and contraction of dead zones, over time illustrating their pulse-like growth and retreat. Through these combined efforts, a global picture of oxygen minimum zones has emerged. We now know that vast, persistent OMZs exist in the open ocean, notably in the eastern tropical Pacific, stretching from the coast of North America down to Chile, and in the Arabian Sea and the Bay of Bengal in the Indian Ocean. These are massive, naturally occurring features, but their extent and intensity are demonstrably increasing due to climate change. Simultaneously, hundreds of smaller but often more intense and biologically devastating coastal dead zones have been mapped in semi-enclosed seas and estuaries around the world. Famous examples include the enormous dead zone in the Gulf of Mexico, driven by the Mississippi River's nutrient load, the persistent deoxygenation in the Baltic Sea, and the recurring events in Chesapeake Bay. Each mapped contour, each shaded region on these scientific visualizations represents a segment of the ocean where life's breath is diminished, a silent testament to profound environmental change. The process of mapping these contours is ongoing, a continuous effort to understand the scale and speed of this silent transformation. It is a slow, methodical unveiling of the ocean's hidden vulnerability. Each data point a whisper from the depths, contributing to a clearer, more comprehensive understanding of where the ocean is losing its breath and how swiftly these silent deserts are expanding. As these intricate scientific processes unfold in your mind, allow the detailed imagery of discovery to gently lull you, guiding you deeper into a state of serene contemplation as the quiet currents of knowledge continue to carry you onward. Surviving on the edge of the breathless realm, as the intricate maps of oxygen minimum zones unfold in our minds, revealing their hidden contours beneath the waves, our quiet contemplation now turns to the very heart of life's struggle within these breathless realms. What happens when the vibrant pulse of marine existence encounters these invisible frontiers, where the vital element of oxygen begins its slow, suffocating retreat? This chapter explores the extraordinary, often desperate measures that life undertakes to survive on the very edge of the void, a testament to evolution's relentless ingenuity and the profound fragility of existence. Imagine a school of shimmering fish, perhaps anchovies or sardines, their collective bodies moving as one, a silver cloud navigating the sunlit waters. Their lives are a constant dance of feeding, avoiding predators, and reproducing, all fueled by a steady supply of dissolved oxygen. As these fish, or any other mobile marine creature, encounter the gradual descent into a hypoxic zone, their sensitive bodies register the change. It is not a sudden dramatic wall, but a subtle, insidious thinning of the very air they breathe. Their gills, designed to efficiently extract oxygen from water, begin to work harder. Their opercula, the bony flaps covering their gills, flaring more frequently, their movements becoming more agitated, then sluggish. For many mobile species, the first and most immediate response is flight. They will actively swim away from the diminishing oxygen, seeking out the oxygenated fringes of these zones. This can involve extensive horizontal migrations, pushing them into unfamiliar territories, or more commonly, vertical migrations where they ascend closer to the oxygen-rich surface waters during the day, only to descend into slightly less hypoxic zones at night to feed if conditions allow. This constant movement, this ceaseless search for breathable water, demands immense energy, diverting resources away from crucial activities like growth and reproduction. It is a life lived on the run, a continuous expenditure of effort just to breathe. This phenomenon creates what scientists call habitat compression, or oxygen squeeze. Picture a vast three-dimensional ocean suddenly having its habitable volume drastically reduced. The oxygen minimum zone acts like an ever-tightening invisible hand, pushing marine life into a narrower band of oxygenated water, often closer to the surface, or confined to shallower coastal areas. This compression has profound consequences. It concentrates populations into smaller spaces, intensifying competition for food and increasing their vulnerability to predators, including fishing vessels. A once dispersed, thriving population becomes an easy target, making their escape a double-edged sword. Yet some species possess remarkable physiological adaptations that allow them to endure, at least for a time, within low oxygen conditions that would be lethal to others. Consider certain species of fish like the hardy gobies found in some coastal dead zones, or specialized crustaceans. Their bodies have evolved to optimize oxygen uptake and utilization. They might possess larger gill surface areas, allowing for more efficient extraction of oxygen from the sparse supply. Their blood might contain specialized hemoglobin, the oxygen-carrying protein, with a much higher affinity for binding oxygen, meaning it can clutch onto oxygen molecules more effectively, even when they are scarce. Some crustaceans, like crabs, utilize hemocyanin, a copper-based protein that also binds oxygen sometimes more effectively than hemoglobin in low oxygen conditions. These adaptations are like having a more powerful, more efficient lung, designed for an atmosphere that is gradually fading. Beyond efficient uptake, these resilient organisms also develop strategies for reduced oxygen consumption. They might lower their metabolic rates, entering a state of physiological slowdown, conserving energy by performing fewer active movements and reducing the demands on their oxygen-starved cells. Imagine slowing your own breathing, your heart rate, your every movement to an almost imperceptible pace, just to make each precious molecule of oxygen last longer. For short periods, some organisms can even switch to anaerobic respiration, a metabolic pathway that does not require oxygen. However, this process is far less efficient and produces lactic acid, which is toxic in large quantities, making it a last-ditch, unsustainable strategy for short bursts of activity, not a long-term solution. For the more sedentary or sessile creatures, those fixed to the seabed or moving very slowly, flight is not an option. Here, the adaptations must be even more profound, a deep rewiring of their very biological machinery. Imagine a clam buried in the sediment or a slow-moving sea star. As the oxygen levels in the surrounding water and sediment plummet, these creatures face an existential threat. Some, like certain species of worms or bivalves, have evolved an extraordinary tolerance for hypoxia. They might possess specialized enzymes that allow their cells to function in the absence of oxygen for extended periods, shifting their metabolism to alternative pathways that are less efficient, but allow for survival. They can enter a state of dormancy, almost a suspended animation, where their metabolic activity drops to incredibly low levels, allowing them to ride out periods of anoxia, waiting for the oxygen to return. It is a slow, patient gamble against the returning tide of breath. Even more remarkably, some organisms form intricate symbiotic relationships with anaerobic bacteria. For instance, certain marine worms or mussels might host these bacteria within their tissues. The bacteria thrive in the oxygen-depleted environment, sometimes using compounds like sulfide as an energy source, and in return, they provide their host with nutrients or detoxify harmful byproducts. It is a partnership forged in the crucible of extreme conditions, a silent agreement to survive together, where neither could easily thrive alone. However, the true masters of the breathless realm are the microorganisms, the bacteria and archaea, that constitute the invisible foundation of life in anoxic zones. These ancient forms of life, many of which predate the great oxidation event, flourish where oxygen is absent. Instead of oxygen, they utilize alternative electron acceptors for respiration, such as nitrate sulfate or even iron. Picture a world where life breathes not oxygen, but other elements, transforming the very chemistry of the water and sediments. In anoxic waters, for example, specialized bacteria perform denitrification, converting nitrate, a common nutrient, into nitrogen gas, which then escapes harmlessly into the atmosphere. other bacteria engage in sulfate reduction using sulfate instead of oxygen, a process that produces hydrogen sulfide, the same toxic, rotten egg-smelling gas that makes these zones so inhospitable to most other life. These microbial processes are not merely passive survival. They are active, transformative forces reshaping the biogeochemistry of the dead zone, creating a distinct, unique ecosystem where life follows entirely different rules. Microbial mats, vibrant, colorful layers of these specialized bacteria, can often be found coating the seafloor in anoxic regions, a stark and simple beauty born from extreme conditions. Yet even with these incredible adaptations, there are limits. The expansion of dead zones, driven by both nutrient overload and a warming climate, is pushing marine life beyond its evolutionary capacity to adapt. Organisms that once thrived in specific niches are finding those niches shrinking, their margins of survival eroding with each passing year. The increased energy expenditure for flight, the reduced growth rates, the diminished reproductive success, and the stress of living on the edge all take a toll on populations. Even the survivors in these zones are often living a compromised existence, their resilience stretched thin. The silent expansion of these breathless realms represents not just a loss of habitat, but a profound alteration of the fundamental conditions that support the vast, complex web of marine life. It is a subtle yet powerful reshaping of the ocean's biological landscape, pushing species to their limits, forcing them to adapt in ways that may not be sustainable in the long term, or simply driving them to extinction in the quiet, suffocating depths. As we conclude this exploration of life's last stand, allow your mind to ponder the extraordinary resilience and adaptability of nature, even in the face of such profound environmental stress. Yet also reflect on the delicate balance that sustains life and how easily that balance can be tipped. Let the quiet contemplation of these struggles and adaptations guide you deeper into a state of serene awareness, as the gentle currents of this knowledge continue to carry you into deeper, more peaceful slumber. Impact on fisheries and marine ecosystems. As our gentle reflection on life's desperate struggle to survive on the very edge of the breathless realm settles within our minds, let us now extend our gaze to the broader consequences of these expanding voids, to the profound and often silent harvest that impacts not only individual species, but entire marine ecosystems and the human communities that depend upon them. The disappearance of oxygen, though unseen, reverberates through the intricate web of ocean life, disrupting ancient patterns and reshaping the very fabric of our blue planet's productivity. Imagine the vast commercial fishing fleets once spreading their nets across thriving, abundant fishing grounds, their vessels guided by generations of accumulated knowledge, seeking out the rich bounty of the sea. Now, as oxygen minimum zones expand, these traditional grounds can become inhospitable, forcing the fish to flee, creating a profound shift in where and how marine life can be found. For highly mobile species such as many commercially important fish, like cod hake or various species of tuna, the immediate response to encroaching hypoxia is often evasion. They detect the subtle yet critical drop in dissolved oxygen and swim away, seeking refuge in the remaining oxygenated waters. This instinctual flight leads to what scientists term habitat compression, or an oxygen squeeze. Picture a vast three-dimensional volume of ocean once fully available to marine life, now being constricted, its breathable space shrinking. The fish, crustaceans, and other mobile invertebrates are forced into increasingly smaller areas of oxygen-rich water, often closer to the surface or confined to shallower coastal zones. This concentration, while initially appearing to be a boon for fisheries, as it makes fish easier to locate and catch in higher densities, is in fact a harbinger of unsustainability. The localized abundance is an illusion, masking a broader decline in overall habitat and population health. These concentrated populations face intensified competition for food, increased stress, and a heightened vulnerability to predation, both from natural predators and from human fishing efforts, which can then rapidly deplete these aggregated stocks. For creatures that are less mobile or entirely sessile, those fixed to the seafloor, the impact of an expanding dead zone is far more immediate and devastating. Consider the vast, silent beds of oysters, clams, and mussels, filtering the water, building intricate reef structures, and providing vital ecological services. Or think of the slow-moving crabs and lobsters that scuttle across the seabed, foraging for food. As a hypoxic or anoxic water mass settles over their habitat, they have no means of escape. Their gills, unable to extract sufficient oxygen, cease to function, and their metabolic processes grind to a halt. The result is widespread mortality, often leading to mass die-offs, where vast numbers of shellfish and bottom-dwelling invertebrates perish, their lifeless bodies sinking into the oxygen-starved sediments. The economic consequences for coastal communities that rely on these shellfish and benthic fisheries can be catastrophic. Imagine the small fishing villages, their livelihoods intricately woven into the rhythm of the tides and the abundance of the sea. A sudden, widespread die-off of oyster beds or crab populations can wipe out years of investment, destroy traditional fishing grounds, and lead to significant job losses, impacting not just individual fishermen, but also seafood processors, distributors, and related tourism industries. The silent harvest is a harvest of emptiness, leaving behind economic hardship and cultural loss. Beyond these direct impacts on commercially valuable species, the expansion of dead zones profoundly disrupts the entire marine ecosystem, from its microscopic foundations to its largest predators. The most immediate ecological consequence is the devastation of benthic communities, the diverse array of life that inhabits the seafloor. These communities, comprising countless species of worms, crustaceans, mollusks, and microorganisms, are the unsung heroes of the ocean, playing crucial roles in nutrient cycling and forming a vital food source for higher trophic levels. When they perish, the seafloor becomes a barren, lifeless expanse, a biological desert where only specialized anaerobic bacteria can survive. This loss reverberates upward through the food web. Fish that feed on bottom-dwelling invertebrates lose their primary food source, forcing them to either migrate or starve further, stressing populations already struggling with reduced habitat. The disruption of nutrient cycling is another critical yet often invisible impact. In healthy oxygenated sediments, nutrients like phosphorus are typically bound to iron and other minerals locked away in a stable form. However, when sediments become anoxic, the chemistry shifts. Iron, in the absence of oxygen, undergoes a chemical transformation, releasing the bound phosphorus back into the water column. This released phosphorus then diffuses upward, acting as a potent fertilizer for surface waters, fueling even more intense algal blooms. This creates a dangerous positive feedback loop. Dead zones cause phosphorus release, which causes more algal blooms, which leads to more organic matter sinking, which consumes more oxygen, thus expanding and intensifying the dead zone. It is a self-perpetuating cycle of environmental degradation, a silent chemical spiral that deepens the void. Furthermore, the loss of oxygen fundamentally alters the nitrogen cycle. While some bacteria in hypoxic zones can convert nitrate into harmless nitrogen gas, denitrification effectively removing nitrogen from the ecosystem, Other processes in anoxic zones can lead to the production of nitrous oxide, a potent greenhouse gas, or even alter the availability of other nitrogen forms in ways that can favor less desirable algal species. The overall result is a less balanced, less resilient nutrient cycle, prone to further instability. Habitat degradation is also a significant consequence. The dense algal blooms fueled by nutrient overload often block sunlight from reaching the seabed. This shading effect can lead to the widespread die-off of crucial underwater habitats like seagrass meadows and kelp forests, which are vital nursery grounds, foraging areas, and protective shelters for countless juvenile fish and invertebrates. Coral reefs, already under immense stress from ocean warming and acidification, are also highly vulnerable to deoxygenation, their delicate polyps unable to survive in low oxygen conditions. The loss of these foundational habitats further diminishes biodiversity and reduces the overall carrying capacity of the marine environment. The long-term impact on marine ecosystems is a gradual shift in species composition and a reduction in overall biodiversity. As oxygen-sensitive species are driven out or perish, the ecosystem becomes dominated by a few hypoxia-tolerant generalists, often including certain types of jellyfish or specialized microbial communities. This simplification of the food web makes the ecosystem less resilient to other environmental stresses, such as pollution disease outbreaks or extreme weather events. A diverse ecosystem with its multitude of species and complex interactions possesses inherent stability. A simplified one is far more fragile, more prone to collapse. Even migratory species, those colossal travelers of the ocean, are impacted. Imagine the long, arduous journeys undertaken by whales, sea turtles, or highly migratory fish, like salmon, navigating vast ocean expanses to reach crucial feeding or breeding grounds. Expanding dead zones can act as invisible barriers, blocking these migratory pathways, forcing animals to take longer, more energetically costly detours, or preventing them from accessing essential habitats. This can impact their reproductive success, their overall health, and the long-term viability of their populations. The silent harvest, therefore, is not just about the fish that are no longer caught. It is about the fundamental transformation of marine life itself. It speaks to a profound ecological shift, a reduction in the ocean's capacity to support its astonishing biodiversity, and a weakening of its natural resilience. The whispers from the depths tell a story of a system under immense stress, where the very breath of life is being slowly, insidiously withdrawn, leaving behind a void that impacts not only the creatures of the sea, but also the human societies that have always looked to the ocean for sustenance, inspiration, and connection. As these far-reaching impacts settle softly in your mind, allow the profound interconnectedness of all life to guide you deeper into a state of serene contemplation as the gentle current of knowledge continues its unhurried journey. The global expansion of the ocean's dead zones. As our contemplation settles upon the profound impacts of breathlessness on individual species and entire marine ecosystems, let us now lift our gaze from localized struggles to embrace a truly planetary perspective. The silent, suffocating voids we have explored are not isolated phenomena confined to a few unfortunate corners of the ocean. Instead, they represent invisible frontiers that are expanding across the globe, a pervasive, quiet transformation, reshaping vast stretches of our blue planet from bustling coastal estuaries to the deep, enigmatic reaches of the open ocean. Imagine a global map, not of land masses and political boundaries, but of the ocean's invisible breath, where healthy, oxygen-rich waters glow with a vibrant, life-sustaining aura. Now picture this map, slowly darkening subtle shadows, creeping across its surface, deepening into vast anoxic stains. This is the reality scientists are meticulously charting: a global deoxygenation, a pervasive retreat of oxygen that manifests in two distinct yet interconnected forms. First, consider the proliferation of coastal dead zones, those regions primarily driven by the relentless flow of nutrient overload from land. These are the zones we have discussed, often found in semi-enclosed seas, estuaries, and continental shelves directly influenced by major river systems and human activities. The Gulf of Mexico, for instance, bears witness to one of the most prominent examples, an immense hypoxic zone that forms annually off the coast of Louisiana and Texas. Imagine its slow seasonal growth stretching for thousands of square kilometers, a vast underwater desert that expands and contracts with the pulse of the Mississippi River's nutrient-laden waters. Each spring and summer, as agricultural runoff intensifies this zone, swells pushing marine life to its boundaries, silencing the vibrant life that once thrived on its seabed. Scientists have observed a clear trend. Not only is this zone recurring, but its average size has been increasing over the decades, a persistent expansion that signals a deepening imbalance. Across the Atlantic, the Baltic Sea offers another stark example. Picture this large, brackish inland sea surrounded by numerous densely populated and agriculturally intensive nations. For decades, the Baltic has struggled with widespread persistent hypoxia, particularly in its deeper basins, which are naturally sluggish in their circulation. Here, the combined burden of nutrient runoff from multiple countries has created vast areas of deoxygenation, some of which are now almost permanently anoxic. Imagine the sea floor of these deep basins, once home to a diverse array of bottom-dwelling creatures, now covered in black, sulfurous mud, a testament to the enduring absence of oxygen. The invisible frontiers here are not just expanding in area, but are deepening, becoming more entrenched, transforming large sections of an entire sea into a silent ecological wasteland. The Black Sea similarly has long been known for its deep anoxic layers, a natural feature exacerbated by human impacts. But even in regions like the Chesapeake Bay in the United States, or the coastal waters of Europe from the North Sea to the Mediterranean, the story is one of increasing frequency, greater intensity, and expanding spatial extent of hypoxic events. Each year, new dead zones are identified, or existing ones are observed to grow larger, persist longer, or form in areas previously unaffected. The cumulative count of these identified coastal dead zones now numbers in the hundreds globally, a stark indicator of a planetary-scale problem driven by local human pressures. These are not merely isolated incidents, but a systemic response of coastal waters to an overwhelming nutrient burden. Then there is the second, equally profound front of global deoxygenation, the expansion and intensification of oxygen minimum zones in the vast open ocean. These are the colossal, naturally occurring OMZs that have existed for millennia, often found in regions of high biological productivity and sluggish deep ocean circulation. Picture the eastern tropical Pacific, a colossal expanse stretching thousands of kilometers along the western coasts of the Americas. This region is home to one of the largest and most intense natural OMZs on Earth, a deep, thick layer of water where oxygen levels are naturally very low. Similarly, the Arabian Sea and the Bay of Bengal in the Indian Ocean host other immense OMZs. What scientists are now observing with increasing clarity through decades of meticulous data collection from Argo floats research vessels and sophisticated models is that these already vast open ocean OMZs are expanding both vertically and horizontally. Imagine these deep, breathless layers thickening, encroaching upon waters that were previously oxygenated, pushing their invisible frontiers outward into the open ocean. The volume of oxygen-depleted water in the open ocean has been estimated to have expanded by several million cubic kilometers over the past half-century, a truly staggering figure that underscores the global scale of this transformation. This open ocean expansion is primarily driven not by nutrient runoff, but by the subtle yet pervasive warming embrace of climate change. Recall how warmer waters hold less dissolved oxygen, and how increased temperature stratification acts like an invisible lid, preventing the vital mixing that would otherwise replenish oxygen in the deeper layers. These physical changes driven by global warming are the primary architects of the open ocean's expanding breathlessness. As the planet's oceans absorb an immense amount of the excess heat trapped by greenhouse gases, these fundamental physical processes are subtly inexorably altered, leading to a widespread global decline in oceanic oxygen content. The consequences of this dual expansion are far-reaching. On both fronts, coastal and open ocean, the invisible frontiers of dead zones are diminishing the habitable volume of the ocean for countless species. Imagine the cumulative effect: a shrinking, breathable space in coastal areas, directly impacting fisheries and local ecosystems, combined with a vast, slow-motion suffocation in the open ocean, disrupting global biogeochemical cycles and impacting highly migratory species. This is not merely a matter of localized environmental degradation, it is a fundamental alteration of the largest living space on Earth. Scientists meticulously track this global expansion using a combination of historical records, modern oceanographic surveys, and sophisticated numerical models. Historical data gathered over decades from research expeditions provides a baseline against which current observations can be compared. Modern tools such as the global network of Argo floats continuously transmit real-time data on oxygen levels from thousands of locations around the world, painting an ever more detailed picture of this silent retreat. These observational data are then fed into complex computer models that simulate ocean circulation chemistry and biology, allowing scientists to project future scenarios and understand the underlying mechanisms driving the expansion. These models consistently predict that if greenhouse gas emissions continue at their current rates, the ocean's deoxygenation will accelerate, and the invisible frontiers of dead zones will continue to expand further into the 21st century and beyond. The sheer scale of this global expansion can be difficult to grasp. Picture the surface area of entire continents. Now imagine that same vastness but underwater, slowly losing its capacity to sustain complex life. The expansion is not always uniform or linear. It can be episodic, influenced by interannual climate variability, but the long-term trend is clear and alarming. The ocean is literally losing its breath molecule by molecule across vast, invisible frontiers. This global deoxygenation is therefore a critical manifestation of planetary change, a profound indicator of the interconnectedness of our atmosphere, our land, and our seas. The invisible frontiers of the dead zones remind us that the ocean is not an infinite, unchanging reservoir, but a dynamic, vulnerable system, responding to the cumulative pressures of human activity on a global scale. As these images of global expansion settle gently in your mind, allow the profound scope of this transformation to deepen your contemplation, guiding you further into a state of serene understanding, as the quiet currents of knowledge carry you onward into peaceful slumber. Dead zones and the climate's intertwined fate. As our awareness gently expands to encompass the global scale of oxygen's retreat, mapping the invisible frontiers of dead zones across our planetary ocean, Our journey now invites us to delve into a more profound and often unseen connection, the intricate cyclical relationship between these breathless realms and the very climate that shapes our world. It is a cycle unseen by the naked eye, a subtle interplay of chemistry and biology that reveals how the ocean's deoxygenation is not merely a consequence of climate change, but also a quiet, insidious contributor to its acceleration, creating a complex, intertwined fate. Imagine the atmosphere above us, a vast, swirling blanket of gases meticulously balanced to sustain life and regulate our planet's temperature. Among these gases are the potent greenhouse gases molecules that trap heat, preventing it from escaping into space, thereby warming the Earth. While carbon dioxide is widely known for its role, other gases produced in the ocean's silent depths also play a significant, though often overlooked part. One such gas is nitrous oxide, or N2O. Picture the depths of an oxygen minimum zone where oxygen levels have dwindled to critically low concentrations, but not yet vanished entirely. In these hypoxic conditions, a specific group of microorganisms, often bacteria and archaea, begin to thrive. These microbes are the architects of a process called denitrification, a vital step in the global nitrogen cycle. Instead of using oxygen for their respiration, they turn to nitrate, a form of nitrogen dissolved in the water, as an alternative electron acceptor. In this complex chemical transformation, a byproduct is often nitrous oxide. Nitrous oxide is a remarkably potent greenhouse gas, far more powerful than carbon dioxide on a per-molecule basis, though it persists for a shorter duration in the atmosphere. Scientists estimate that it possesses a global warming potential approximately 265 times greater than carbon dioxide over a 100-year timescale. Thus, as oxygen minimum zones expand and intensify globally, the ocean's capacity to produce and release more of this powerful greenhouse gas quietly increases. Imagine the subtle, invisible plumes of N2O rising from the breathless depths, slowly, steadily adding to the atmospheric blanket, contributing to the very warming that initiated the deoxygenation in the first place. It is a slow, insidious feedback loop working unseen beneath the waves. Even deeper, or in the most intensely anoxic pockets of the dead zones where oxygen is entirely absent, another potent greenhouse gas can be generated, methane, or CH4. In these truly breathless sediments and water columns, a different community of microorganisms known as methanogens comes to life. These ancient, resilient microbes thrive in the complete absence of oxygen, breaking down organic matter through a process called methanogenesis, producing methane as a byproduct. Methane is an even more potent greenhouse gas than nitrous oxide, possessing a global warming potential about 84 times greater than carbon dioxide over a 20-year period. While most of the methane produced in deep anoxic sediments is typically consumed by other microbes before it reaches the atmosphere, some of it can escape, particularly in shallow coastal dead zones or during periods of intense stratification. Imagine bubbles of this powerful gas slowly rising from the seafloor, making their way through the water column and eventually breaching the surface, adding another subtle yet significant contribution to the atmospheric greenhouse effect. The expansion of anoxic areas therefore potentially creates more environments conducive to methane production, further intertwining the fate of dead zones with the trajectory of global warming. Beyond these direct emissions of potent greenhouse gases, ocean deoxygenation also profoundly impacts the global carbon cycle, altering the ocean's capacity to absorb and store carbon dioxide from the atmosphere. The ocean is by far the largest active carbon sink on Earth, having absorbed approximately 1/4 of the carbon dioxide emitted by human activities since the Industrial Revolution. This absorption helps to regulate atmospheric CO2 levels, mitigating the rate of climate change. A crucial mechanism for this carbon sequestration is the biological pump. Picture the tiny phytoplankton in the sunlit surface waters, photosynthesizing and absorbing carbon dioxide. When these organisms die or are consumed by zooplankton, which then excrete carbon-rich fecal pellets, this organic matter slowly sinks into the deep ocean. This downward flux of carbon away from the surface and into the depths is a vital process for removing carbon dioxide from the atmosphere and storing it in the ocean's vast interior. However, dead zones disrupt this delicate pump. In oxygen-depleted waters, the efficiency of the biological pump can be altered, while anoxic conditions can sometimes lead to better preservation of organic carbon in sediments, preventing its immediate decomposition and release of CO2. This is often outweighed by other factors. For example, the shift in microbial communities in dead zones can lead to the release of dissolved organic carbon DOC back into the water column, which can eventually be consumed by other microbes and release CO2. Moreover, the overall reduction in biodiversity and productivity in dead zones can diminish the amount of carbon initially fixed by photosynthesis, thereby reducing the overall efficiency of the biological pump in capturing atmospheric CO2. Furthermore, the warming that drives deoxygenation also directly reduces the ocean's physical capacity to absorb carbon dioxide. Remember that colder water holds more dissolved gases, including CO2. As the ocean warms, its ability to take up atmospheric CO2 diminishes, leaving more of it in the atmosphere. This creates another critical feedback. The same warming that expands dead zones also weakens the ocean's role as a carbon sink, leading to higher atmospheric CO2 concentrations and thus more warming. It is a complex reinforcing loop where each negative change exacerbates the other, pushing the system further out of balance. The intertwined fate of dead zones and climate also extends to the very stability of ocean ecosystems, which in turn influences their capacity to buffer climate change. Healthy, diverse marine ecosystems are more resilient and more efficient at cycling nutrients and carbon. The simplification of food webs and the loss of biodiversity within dead zones as oxygen-sensitive species perish or flee reduces the overall health and functionality of these ecosystems. This weakened state means they are less capable of performing their vital roles in global biogeochemical cycles, including the regulation of atmospheric gases. Think of the vast interconnected cycles of Earth like invisible gears, turning within a colossal clockwork mechanism. The expansion of dead zones represents a grinding of these gears, a disruption in the smooth, balanced flow of elements. The release of potent greenhouse gases like nitrous oxide and methane from these breathless realms, coupled with the diminished capacity of a deoxygenated ocean to absorb carbon dioxide, creates a powerful positive feedback loop. This means that the problem of dead zones, initially seen as a consequence of climate change and nutrient pollution, actively contributes to and accelerates global warming, thereby creating even more deoxygenation. It is a self-reinforcing spiral of environmental degradation, a cycle unseen by human eyes, but profoundly felt across the planet. Scientists are diligently working to quantify these feedback mechanisms, using sophisticated models to understand the precise contribution of oceanic N2O and CH4 emissions to the global greenhouse gas budget, and how changes in ocean oxygen levels will affect future carbon sequestration. These are complex calculations involving intricate interactions between physical, chemical, and biological processes. But the emerging picture is clear. The ocean's breath is deeply, inextricably linked to the planet's climate, and the health of one profoundly influences the other. As these profound and intricate cycles unfold in your mind, allow the deep interconnectedness of Earth's systems to settle softly within you. The ocean is not merely a passive recipient of human impact. It is an active participant in planetary processes, and its silent struggles in the breathless realms send ripples through the very atmosphere we breathe. Let this contemplation of the unseen cycles guide you deeper into a state of serene understanding as the gentle currents of knowledge continue to carry you into peaceful, restorative slumber. Science, surveillance, and the quest for solutions. As our awareness gently expands to encompass the global scale of oxygen's retreat, mapping the invisible frontiers of dead zones across our planetary ocean, our journey now invites us to delve into a more profound and often unseen connection, the intricate cyclical relationship between these breathless realms and the very climate that shapes our world. It is a cycle unseen by the naked eye, a subtle interplay of chemistry and biology that reveals how the ocean's deoxygenation is not merely a consequence of climate change, but also a quiet, insidious contributor to its acceleration, creating a complex, intertwined fate. Imagine the atmosphere above us, a vast, swirling blanket of gases meticulously balanced to sustain life and regulate our planet's temperature. Among these gases are the potent greenhouse gases molecules that trap heat, preventing it from escaping into space, thereby warming the Earth. While carbon dioxide is widely known for its role, other gases produced in the ocean's silent depths also play a significant, though often overlooked part. One such gas is nitrous oxide, or N2O. Picture the depths of an oxygen minimum zone where oxygen levels have dwindled to critically low concentrations, but not yet vanished entirely. In these hypoxic conditions, a specific group of microorganisms, often bacteria and archaea, begin to thrive. These microbes are the architects of a process called denitrification, a vital step in the global nitrogen cycle. Instead of using oxygen for their respiration, they turn to nitrate, a form of nitrogen dissolved in the water, as an alternative electron acceptor. In this complex chemical transformation, a byproduct is often nitrous oxide. Nitrous oxide is a remarkably potent greenhouse gas, far more powerful than carbon dioxide on a per-molecule basis, though it persists for a shorter duration in the atmosphere. Scientists estimate that it possesses a global warming potential approximately 265 times greater than carbon dioxide over a 100-year timescale. Thus, as oxygen minimum zones expand and intensify globally, the ocean's capacity to produce and release more of this powerful greenhouse gas quietly increases. Imagine the subtle, invisible plumes of N2O rising from the breathless depths, slowly, steadily adding to the atmospheric blanket, contributing to the very warming that initiated the deoxygenation in the first place. It is a slow, insidious feedback loop, working unseen beneath the waves. Even deeper, or in the most intensely anoxic pockets of the dead zones, where oxygen is entirely absent, another potent greenhouse gas can be generated, methane or CH4. In these truly breathless sediments and water columns, a different community of microorganisms known as methanogens comes to life. These ancient resilient microbes thrive in the complete absence of oxygen breaking down organic matter through a process called methanogenesis, producing methane as a byproduct. Methane is an even more potent greenhouse gas than nitrous oxide, possessing a global warming potential about 84 times greater than carbon dioxide over a 20-year period. While most of the methane produced in deep anoxic sediments is typically consumed by other microbes before it reaches the atmosphere, some of it can escape, particularly in shallow coastal dead zones or during periods of intense stratification. Imagine bubbles of this powerful gas slowly rising from the seafloor, making their way through the water column and eventually breaching the surface, adding another subtle yet significant contribution to the atmospheric greenhouse effect. The expansion of anoxic areas therefore potentially creates more environments conducive to methane production, further intertwining the fate of dead zones with the trajectory of global warming. Beyond these direct emissions of potent greenhouse gases, ocean deoxygenation also profoundly impacts the global carbon cycle, altering the ocean's capacity to absorb and store carbon dioxide from the atmosphere. The ocean is by far the largest active carbon sink on Earth, having absorbed approximately 1/4 of the carbon dioxide emitted by human activities since the Industrial Revolution. This absorption helps to regulate atmospheric CO2 levels, mitigating the rate of climate change. A crucial mechanism for this carbon sequestration is the biological pump. Picture the tiny phytoplankton in the sunlit surface waters photosynthesizing and absorbing carbon dioxide. When these organisms die or are consumed by zooplankton, which then excrete carbon-rich fecal pellets, this organic matter slowly sinks into the deep ocean. This downward flux of carbon away from the surface and into the depths is a vital process for removing carbon dioxide from the atmosphere and storing it in the ocean's vast interior. However, dead zones disrupt this delicate pump. In oxygen-depleted waters, the efficiency of the biological pump can be altered. While anoxic conditions can sometimes lead to better preservation of organic carbon in sediments, preventing its immediate decomposition and release of CO2. This is often outweighed by other factors. For example, the shift in microbial communities in dead zones can lead to the release of dissolved organic carbon DOC back into the water column, which can eventually be consumed by other microbes and release CO2. Moreover, the overall reduction in biodiversity and productivity in dead zones can diminish the amount of carbon initially fixed by photosynthesis, thereby reducing the overall efficiency of the biological pump in capturing atmospheric CO2. Furthermore, the warming that drives deoxygenation also directly reduces the ocean's physical capacity to absorb carbon dioxide. Remember that colder water holds more dissolved gases, including CO2. As the ocean warms, its ability to take up atmospheric CO2 diminishes, leaving more of it in the atmosphere. This creates another critical feedback. The same warming that expands dead zones also weakens the ocean's role as a carbon sink, leading to higher atmospheric CO2 concentrations and thus more warming. It is a complex reinforcing loop where each negative change exacerbates the other, pushing the system further out of balance. The intertwined fate of dead zones and climate also extends to the very stability of ocean ecosystems, which in turn influences their capacity to buffer climate change. Healthy, diverse marine ecosystems are more resilient and more efficient at cycling nutrients and carbon. The simplification of food webs and the loss of biodiversity within dead zones as oxygen-sensitive species perish or flee reduces the overall health and functionality of these ecosystems. This weakened state means they are less capable of performing their vital roles in global biogeochemical cycles, including the regulation of atmospheric gases. Think of the vast interconnected cycles of Earth like invisible gears, turning within a colossal clockwork mechanism. The expansion of dead zones represents a grinding of these gears, a disruption in the smooth, balanced flow of elements. The release of potent greenhouse gases like nitrous oxide and methane from these breathless realms, coupled with the diminished capacity of a deoxygenated ocean to absorb carbon dioxide creates a powerful positive feedback loop. This means that the problem of dead zones, initially seen as a consequence of climate change and nutrient pollution, actively contributes to and accelerates global warming, thereby creating even more deoxygenation. It is a self-reinforcing spiral of environmental degradation, a cycle unseen by human eyes, but profoundly felt across the planet. Scientists are diligently working to quantify these feedback mechanisms, using sophisticated models to understand the precise contribution of oceanic N2O and CH4 emissions to the global greenhouse gas budget, and how changes in ocean oxygen levels will affect future carbon sequestration. These are complex calculations involving intricate interactions between physical, chemical, and biological processes. But the emerging picture is clear: the ocean's breath is deeply, inextricably linked to the planet's climate, and the health of one profoundly influences the other. As these profound and intricate cycles unfold in your mind, allow the deep interconnectedness of Earth's systems to settle softly within you. The ocean is not merely a passive recipient of human impact. It is an active participant in planetary processes, and its silent struggles in the breathless realms send ripples through the very atmosphere we breathe. Let this contemplation of the unseen cycles guide you deeper into a state of serene understanding, as the gentle currents of knowledge continue to carry you into peaceful, restorative slumber. A future shaped by our silent choices. As our deep contemplation traces the intricate, unseen cycles that bind the ocean's breath to the planet's very climate, revealing their intertwined fate, we arrive at a profound realization: the trajectory of these silent, suffocating voids is not an unchangeable destiny. The future of the ocean's dream, its capacity to once again breathe freely and sustain its astonishing biodiversity, is ultimately shaped by the silent collective choices we make, beginning in this very moment. The darkness we have charted is not absolute. Within its depths lies the quiet promise of renewal, guided by human ingenuity and a renewed sense of stewardship. Imagine, if you will, a future where the rivers, once burdened with an overwhelming flow of nutrients, now carry only a gentle, balanced sustenance to the sea. This vision begins far upstream on the vast expanses of agricultural land that feed our growing world. Instead of broad, indiscriminate applications of synthetic fertilizers, picture a meticulous, almost artistic approach to farming. This involves precision agriculture, where satellite imagery, drone technology, and soil sensors allow farmers to apply nutrients with pinpoint accuracy, delivering precisely what the crops need, exactly when they need it, thereby minimizing runoff. Envision fields where cover crops planted between growing seasons act like living sponges, holding valuable nutrients in the soil, preventing them from washing away with the rains. Further downstream, imagine the gentle undulations of healthy riparian buffers, wide verdant strips of native vegetation lining the banks of streams and rivers. These natural filters, with their deep root systems, would intercept and absorb excess nutrients before they ever reach the waterways, acting as a living, breathing barrier against pollution. Picture wetlands restored to their ancient glory, their marsh grasses and dense vegetation forming intricate biological filters, naturally purifying water as it slowly seeps through their rich, organic soils before flowing into estuaries. These are not grand, dramatic interventions, but subtle systemic shifts in land management, designed to restore the natural balance, allowing the land to once again hold its burden rather than releasing it to the sea. In our urban landscapes, the vision extends to a future where our wastewater, once a source of pollution, becomes a resource. Imagine advanced wastewater treatment facilities not merely removing solids but meticulously stripping out dissolved nitrogen and phosphorus to extremely low concentrations, ensuring that the water returned to rivers and coastal areas is clean and pure. Envision cities embracing green infrastructure permeable pavements that allow rainwater to soak into the ground rather than rushing into storm drains. Green roofs adorned with vegetation that absorb precipitation and strategically placed rain gardens that capture and filter runoff. These are interventions that mimic nature's own processes, transforming urban areas into more harmonious, less impactful contributors to the marine environment. These localized land-based solutions, while requiring significant investment and collective effort, hold the quiet power to reverse the expansion of coastal dead zones. Scientists have observed promising signs in areas where such measures have been rigorously implemented. For example, in some parts of the Chesapeake Bay, targeted nutrient reduction strategies have led to measurable improvements in oxygen levels in certain areas, allowing some benthic communities to slowly begin their return. These are small yet profound victories, demonstrating that the breath of the ocean can indeed be restored one watershed at a time, one careful choice at a time. However, the fate of the open ocean dead zones and the global retreat of oxygen is inextricably linked to the broader challenge of climate change. Here, the solutions demand a planetary-scale transformation. Imagine a world powered not by the ancient, heat-trapping energy of fossil fuels, but by the clean, boundless energy of the sun and the wind. Picture vast solar farms shimmering under the sun, their silent panels converting light into power, and elegant wind turbines spinning gracefully against the sky, harnessing the invisible currents of the air. This transition to renewable energy sources, coupled with aggressive energy efficiency measures in our homes, industries, and transportation systems, is the fundamental choice that will determine the future of ocean oxygenation. Every kilowatt-hour of renewable energy generated, every unit of energy saved, contributes to a reduction in greenhouse gas emissions, thereby slowing the warming of our planet. As the atmospheric blanket of heat-trapping gases gradually thins, the ocean will slowly begin to stabilize its temperature. This will in turn reduce the enhanced stratification that traps oxygen in surface waters and allow the ocean to regain its natural capacity to hold dissolved oxygen. It is a slow, majestic process of planetary healing, a gradual rebalancing of Earth's fundamental systems, guided by our collective commitment to a sustainable future. Beyond these foundational shifts, scientists are also exploring ocean-based solutions that can help mitigate climate change and support ocean health. Picture vast, healthy coastal ecosystems like mangrove forests, salt marshes, and seagrass meadows, often termed blue carbon habitats. These vibrant ecosystems are incredibly efficient at capturing and storing atmospheric carbon dioxide, locking it away in their biomass and sediments for centuries. Protecting and restoring these blue carbon ecosystems not only helps to mitigate climate change, but also provides crucial habitat for marine life and buffers coastlines against storms, contributing to a more resilient, breathing ocean. The quest for solutions also relies on the continuous, unwavering dedication of science and surveillance. Imagine the global network of Argo floats underwater gliders and oceanographic moorings tirelessly collecting data, their silent signals transmitting the ocean's vital signs back to us. This ongoing monitoring is crucial for understanding the effectiveness of our actions, for charting the slow, subtle improvements, and for identifying new challenges as they emerge. Scientists continue to refine their models, deepening our understanding of the complex feedback loops between deoxygenation and climate change guiding our choices with ever greater precision. Ultimately, the ocean's dream is a dream of balance, of resilience, and of breath. It is a vision where human societies live in harmony with the natural world, recognizing that the health of the vast blue depths is inextricably linked to our own well-being. It is a future where the silent choices we make today, from the way we farm our land to how we power our lives, resonate through the currents, shaping an ocean that can once again breathe freely. The path forward is long, and the challenges are immense, but the quiet promise of a healthier, more vibrant ocean sustained by a renewed respect for its delicate balance remains a powerful guiding light. The journey towards this future has already begun, powered by the collective will to listen to the ocean's whispers and to respond with thoughtful, deliberate action. And so, as we drift away from the profound depths of the ocean's silent deserts, allow the vastness of these liquid realms to dissolve into the quietude of your own inner world. Consider how the very atoms that form your being, the carbon and oxygen that once flowed through ancient seas and stellar nurseries, echo this planetary rhythm, connecting you intimately to every breath taken by the ocean. Just as the deep currents carry unseen mysteries, so too does your mind prepare to journey into its own profound, unseen currents of dreams where thoughts and sensations gently ebb and flow. May the deep, restorative currents of the dreaming ocean carry you gently into the profound stillness of sleep, guiding you to a peaceful, breathless rest. Good night.